Welcome to this presentation on the speed of light and atomic behaviour. Back in 1979, when I was 37 years old, a friend of mine knew of my interest in scientific anomalies and also of my interest in astronomy. He sent me a book entitled Mysterious Universe, a handbook of astronomical anomalies. An anomaly is something in which science with their theories are in disagreement with the data. The two do not gel. And as a consequence of this, I found this book extremely interesting. In fact, it was fascinating. Here's the cover of that book. Near the end of this book, I came across something bizarre. While I was at university, I had been taught, as we were all taught, and are still being taught, that the speed of light in a vacuum has been constant through time. In physics, the speed of light is often designated by the letter c, ABC, and it is usually assumed that c, the speed of light, is constant. But here in this book were tables and articles which showed a systematic downward progression in the speed of light. Generally, each new measurement was lower than the previous one. Investigation revealed that these changes in light speed had been discussed for an extended time by a number of very competent physicists, starting in the mid-19th century and going on until the mid-20th century. The differences, though relatively small, were nonetheless significant. They caused ongoing comment in the scientific journals for many years as new and progressively lower measurements were made. Intrigued, I thought it might take me a couple of weeks to find whether it had been mechanical or human error which led to these differences. Interestingly though, article after article in peer-reviewed science journals were quoted and referenced, discussing these changes in measurements. I was able to find the articles themselves along with the reports of the original experiments. I also found the comments from those doing the experiments. The decreasing speed of light turned out to be hard to dismiss either easily or simply. Professor Raymond T. Burge of the University of California, Berkeley, shown here, was one of the physicists involved in these discussions in the first half of the 20th century. He was referred to as the keeper of the constants. He had charted not only the measured changes in the speed of light, but he had also kept track of changes involving some of the other processes of atomic physics, which had been considered fixed quantities as well. These are called atomic constants, and a number of them were varying systematically along with the speed of light. This graph displays Burge's own recommended values for the speed of light. Even though Burge did not believe that any change in the speed of light was possible, he had to acknowledge that the data revealed a decline in the measured value. There is another constant measured as changing at the same time, something known as Planck's constant, designated by the letter h. This was changing in the opposite direction. It was systematically increasing. In 1911, physicist Max Planck had pointed out that this quantity h, which now bears his name, was a measure of the strength of the zero-point energy. The increase in Planck's constant h seemed to be in inverse proportion to the speed of light. In discussing the data measuring h, Professor J.H. Sanders pointed out in 1965 that the increasing value of Planck's constant can only partly be accounted for by the improvements in instrumental resolution and changes in the accepted value of other constants. It appeared that a genuine increase in Planck's constant h was in fact occurring. Furthermore, electron and other atomic masses m were measured as increasing as well. All these measurements and the ongoing discussions were listed in the major scientific journals. These and other associated data indicated that, even with all the measured changes, energy was still being conserved in the process. This means there were no changes in the total energies of the systems involved, even though the constants describing those systems were measured as changing. My curiosity was piqued. What was going on? This led to what is now almost 40 years of research in which I have come to the conclusion, as have a number of others, that these changes were and are real. But the scientific community, for the most part, still holds to the older idea that the speed of light and some of the other physical measurements have remained constant through time. So let's look at what the experiments have actually found and the subsequent discussions, and see if we can find out what has really been happening. Professor Sanders and others had analysed Planck's constant and the experiments involved to see if they could pinpoint a cause for the changes. In the same way, Professor N.E. Dorsey, pictured here, did an extensive analysis on the Lightspeed data in the early 1940s. Dorsey attempted to show the trend in light speed was due to experimental problems and improved equipment. Despite detailed analyses, he did not find those flaws. Ultimately, all he could do was to extend the possible error ranges of the final published values. But even this did not eliminate the declining trend in the data, which he personally described as being monotonous. The results from Pulkovo Observatory in Russia also showed that simple errors in equipment or human measurements were not responsible for this apparent change in the speed of light. There, the same equipment was used from 1840 to 1940 by a group of astronomers observing over their own lifetimes. There are a number of ways in which the speed of light can be measured. They used the same method, which measures angles rather than distances and times, for the entire period. The graph of the Pulkovo results reveals a consistent downward trend, which could not be due to changing equipment or measurement techniques. Yet the downward trend is very much in evidence. In all, 20 determinations of light speed were made. Each determination involved over 10,000 sets of observations, so over 200,000 separate observations were involved. The reliability of this trend can be assessed mathematically. The bars you see on either side of the dots on the graph show that there might be an error extending that far to either side of the measurement. These are called error bars. But even if all the possible errors are considered, the speed of light is still measured as decreasing. When a trend such as the possible decreasing speed of light is being considered scientifically, it is extremely rare that the probability is considered to be 100% certain. Until recently, however, the truth of a trend was accepted if the risk of being wrong was less than 1 in 20. Recently, that restriction has become tighter, and the probability now has to exceed the chance that it is wrong less than 1 time in 200. Even so, it is almost unheard of for any scientist requiring a data trend to have a probability of better than 1 chance in 1,000 of being wrong before it's accepted. Yet the Pulkovo data suggest a decay trend with less than 1 chance in 10,000 of being wrong. The speed of light was decreasing. Until 1675, it was thought that light travelled at an infinite speed. In other words, it moved instantaneously. In that year, Roemer showed it was not the case. Using early telescopes, scientists had measured the amount of time one of Jupiter's moons, Io, took to travel around its planet. They timed the eclipses when Io went behind Jupiter and disappeared, or when it emerged on the other side of Jupiter. But it was also seen that those predicted eclipse times seemed to lengthen as the Earth and Jupiter in their orbits increased in distance from each other. The difference in timing, Roemer reasoned, was due to the time it took for light to travel across the diameter of the Earth's orbit. Roemer used these observations to show that the speed of light was a definite speed and not infinite. As the two planets drew away from each other, the time to cross the distance between them increased. Then, as they grew closer together again, the time decreased. However, for 3 reasons, Roemer's calculation of light speed cannot be considered today. The first is that they depended on visual inspection of eclipse times, and that is very subjective, and had a typical variation of at least 20 seconds. The second is that Io's orbit is elliptical, and so its speed in its orbit varies. The third is that our spacecraft and modern observations have shown that Io's orbit is continually and measurably changing. This is due to Io's gravitational and magnetic interaction with Jupiter and with two of its neighbouring moons. This means that we cannot cross-check Roemer's data from over 300 years ago with today's observations. Discounting all values obtained by those using Roemer's method, there have been 155 determinations of light speed by 15 different methods, each involving thousands of individual experiments. The graph of the results of those experiments, with errors less than 0.1%, is shown here. These are the measurements starting from 1726, which were made using special equipment. From this graph, it can be seen that there is consistent decline in the value of light speed, rather than a random distribution of results around a fixed value. Each of the 15 methods of measurement show a statistical decline, just as the Pulkovo results do. All 155 determinations together also show a decline. Statistician Alan Montgomery and physicist Lambert Dolphin did an independent analysis. They re-examined all the data and confirmed that there was a decline in the value of C that was statistically significant. The trend was significant at the 95% confidence interval or better. Their analysis was published in a peer-reviewed science journal in 1993. In 1931, the French astronomer Émile Goury-Debray wrote in a science journal Nature, quote, "If the velocity of light is constant, how is it that, invariably, new determinations give values which are lower than the last one obtained? There are 22 coincidences in favour of a decrease in the velocity of light, while there is not a single one against it." End quote. Goury-Debray continued by saying something that is still relevant today. Quote, "I believe that in any other field of inquiry, such a discrepancy between observation and theory would be felt intolerable. Why it has suffered in the present case is not apparent. It is, however, certain that if a decrease in the velocity of light were accepted on theoretical grounds, and if some misguided physicist attempted to demonstrate that it is constant, the present observations would be called to witness to silence him conclusively." End quote. Remember Professor Burge, the keeper of the constants. Despite the measurements, he did not accept a changing speed of light. He had charted it, but he did not accept it. To understand his objection, we need to understand a little about light waves. The colour of light is determined by the length of the light wave, that is, the distance from one wave crest to the next. The brightness of the colour is determined by the height of the wave. Burge's reason for rejecting a decline in light speed was related to the fact that colours themselves remain the same through time, meaning that wavelengths have not changed. If they had, there are instruments that could pick that up. Burge noted that wavelengths and length standards were experimentally proven to be unchanged with time. He then concluded that, and I quote, "If the value of C is actually changing with time, but the value of wavelength in terms of the standard meter shows no corresponding change, then it necessarily follows that the value of every atomic frequency must be changing. Such a variation is obviously most improbable." End quote. We know that the speed of light is equal to the frequency or number of waves past a given point in a given amount of time, multiplied by the wavelength of the light involved. So what Burge is saying here is that, since wavelengths are not changing as the speed changes, this can only mean that the frequency changes by the same proportion that the speed changes. The reason Burge connected the speed of light with other atomic frequencies is because emission of photons of light from an atom do indeed depend on other atomic processes and atomic frequencies. Atomic processes must therefore be changing in the same proportion that the speed of light was changing. But Burge thought it was improbable that any atomic frequencies were changing synchronously with the speed of light. This would require, among other things, that the rate at which electrons circled the atomic nucleus would be proportionally faster when the speed of light was higher. This could lead to problems with accepted ideas. The discussions regarding the possible changes in some atomic constants and the speed of light had been going on in a number of peer-reviewed journals for almost 100 years. Then Burge, the keeper of the constants, wrote a startling introduction to an article in August of 1941. Note that the emphasis is his own. I quote, "This paper is being written on request and at this time on request. In spite of the delusive word constant appearing in the title, it is the continual variation in the value of these quantities that furnishes most of the interest in the subject. It would indeed be disheartening to any real scientist to feel that an accepted value of any physical constant would never again be changed. The most characteristic feature of science in general and in particular is its never-ending change. But what one must not overlook is the fact that it is the probable value of any given constant that changes, not its actual value. A belief in any significant variability of the constants of nature is fatal to the spirit of science as science is now understood." End quote. This article effectively shut down all discussion about a possible change in the speed of light. From the 1940s onward, it has been accepted and taught that the speed of light, c, is a constant. Let's take a look now at those lines of evidence that contradict Burge's claim regarding the constancy of c. He knew about the first one and knew enough about the second one to have given it serious consideration. The first line of evidence Burge certainly knew about. It concerns something called the fine structure constant, or alpha. The original designation of alpha was defined as the velocity of the electron in the lowest orbit, the orbit closest to the nucleus, divided by the velocity of light. The data indicated that alpha was an unchanging quantity. This means that the speed of light and the speed of the electron were in lockstep with each other. There were two options. Both quantities could have remained the same since the beginning, but the same result happens if they are each changing in perfect proportion to one another. As long as the relationship is constant, alpha is constant. Burge knew that. He knew that alpha being a constant did not have only one possibility, but the only option he would accept was the one which required both light speed and electron orbital speed to be fixed quantities. He would not even consider the option in which light speed and electron orbital speed were changing in exact proportion to each other. The second line of evidence involves the fact that there are two ways of keeping time. One we are familiar with in our daily lives is orbital time, how long it takes for the Earth to go around the Sun or the Moon to go around the Earth. This form of timekeeping depends on gravity. The second way of keeping time is through the measurement of atomic processes or atomic frequencies, such as the time it takes an electron to go once around its nucleus. Gravitational time gives us enough to live our lives by in terms of hours, minutes, and even seconds. However, atomic time or atomic frequencies can determine very much smaller quantities of time, and that is very useful in some fields of science. Professor Burge knew that there were two possible ways to measure time. He absolutely refused to consider that these two clocks might run at different rates. If they did run at different rates, then a lot of scientific calculations would have to be reconsidered. He was right, but let's look at the observational evidence that has been accumulated since his time. As mentioned earlier, Planck's constant, known as h, is a measure of the strength of the zero-point energy. Burge himself had noted that the values of Planck's constant were increasing. Later, in 1965, astrophysicist Jean Kovalevsky of Paris Observatory pointed out that if Planck's constant h was changing, then atomic frequencies would also be changing when compared with orbital clock rates, called the orbital standard. In fact, increasing values of h implied that the atomic clock, in all its various forms, was slowing down when compared to the orbital clock. Others have also pointed out that the data from other constants suggest that atomic and orbital clocks may be running at different rates. Gravity itself is unchanging through time. This means that time, as measured by gravity, our orbital clock, has been ticking at a constant rate. This is in contrast to the possibility that atomic times might have changed. Dr. Thomas Van Flandern of the US Naval Observatory, Washington, did a series of measurements of atomic clock rates compared with the orbital standard. Van Flandern collected data from 1955 to 1981 using lunar and planetary laser ranging. After his study, Van Flandern concluded that, and I quote, "The number of atomic seconds in an orbital interval is becoming fewer. Presumably, if the result has any generality to it, this means that atomic phenomena are slowing down with respect to orbital phenomena." End quote. Other observatories have conducted similar investigations. Data by Yuri Kolesnik for the planets Mercury, Venus and the Sun show the trend well. An analysis by C.J. Masreliers in 2004 concluded that, and I quote, "The planetary drifts Kolesnik and several other investigators have detected are based on accurate modern observations, and they use atomic time. Therefore, those drifts are unquestionably real." End quote. Atomic and orbital time appeared to be running at different rates. The graph on the screen at the moment is plotted from the data given by Yuri Kolesnik. It shows the progression of orbital time in years horizontally and the corresponding data in atomic time for the planet Mercury on the vertical axis. These two measurement sets were taken very simply. One is done by timing Mercury's astronomical events using our orbital calendar and mechanical watches or clocks, and the other way measures events, these same events, using atomic time and atomic clocks. These two measurements have not stayed together, but have drifted apart. This graph confirms that the atomic clock has slowed compared with the orbital standard. If you remember, Burge had objected to the idea that the speed of light was changing, because that would indicate a change in other atomic processes as well. He considered that option to be somewhere between impossible and highly improbable. However, we can see now that other atomic processes have shown change, so this objection by Burge is overruled by the more recent data. Measurements, and very accurate ones, have shown that not everything in science used to consider as a constant has indeed been a constant. On the other hand, some combinations of constants have proved to be invariant. For instance, Planck's constant h and the speed of light c, when multiplied together, have been shown to always give the same number. This data comes from astronomical observations all through the universe, even to the most distant parts. But consider, this does not necessarily mean that each by itself has been invariable. What it does mean is that if one changes, the other has also changed, but in the opposite direction. It's like the number 12. You can get 12 several ways. 1 times 12, 2 times 6 and 4 times 3. Note that if one number doubles, the other halves. So there is always the possibility that everything has stayed the same. But when the measurements themselves show a change, yet the final result is invariant, we have to accept that these changes are in tune with each other or synchronous. So in terms of HC, H must be proportional to 1 over C exactly. There are other examples where this sort of synchronous relationship can be seen. The relationship between electron mass m and Planck's constant h is expressed as m over h squared in some quantities. This relationship always results in the same number. It's invariant. But again, this doesn't mean that either m or h squared has to remain constant, only that if one changes, the other is changing in a direct proportion to it. Now watch. This behaviour of m indicates that all atomic masses like m were proportional to h squared. But h is proportional to 1 over c, right? This means that if both are squared, h squared is proportional to 1 over c squared. When we put this together, that means atomic masses m are proportional to 1 over c squared. So as m changes, then c squared is changing in inverse proportion. This means that mc squared is fixed. Now look at that famous equation, E equals mc squared. Since mass and the c squared term are in inverse proportion to each other, that means that energy E is always conserved. You don't gain or lose energy as mass and the speed of light change. Indeed, these relationships all show that energy is being conserved as the physical constants vary. Laboratory experiments involving reaction energies of atomic particles have confirmed that this is true. At this point, we can see the actual data show that some of what has been considered constants are in fact changing in value. This is not often mentioned in university courses, but the data is there. Indeed, if the speed of light is excluded, confirmatory trends appear in 475 measurements of 11 other atomic quantities. Why is this happening? We might also ask if there is a single common factor involved in all these changes. Let's look at a few clues. The first clue was from physicist Max Planck. He wrote 2 very important papers in the early years of the 20th century. In the first paper in 1901, he introduced a mathematical term to answer a problem that physicists were having. But at that point, it was only a mathematical term. Planck was not satisfied with just inserting a term to get the mathematics right. So he kept working. Then in his second paper in 1911, he identified that term as having a real physical meaning. That term is now called Planck's constant and is usually designated as the letter H. There, in that 1911 paper, he pointed out that Planck's constant H was a measure of the strength of the vacuum zero-point energy, the ZPE. The measurements of Planck's constant started in the 1920s and subsequently showed that it was not constant but increasing. Since Planck's constant was increasing, this implied that the ZPE strength was also increasing. The zero-point energy was discussed in the second video in this series. In that session, it was shown to be the result of an expanding universe. Energy is put into the fabric of space as it expanded, in the same way as energy is put into the fabric of a balloon being inflated. In space, this energy appears as the zero-point energy, the ZPE. As the universe continued to expand, the strength of the ZPE continued to build up. To refresh your memory further, the zero-point energy consists of a massive number of electromagnetic waves that permeates all of space. These waves consist of all wavelengths, but the vast majority are on the shorter end of the spectrum. So the first clue, the increasing value of Planck's constant H, leads us to suspect the increasing ZPE strength may be responsible for all of the observed changes, since h is a direct measure of the ZPE strength. The second clue requires us to understand the effects of the zero-point energy on subatomic masses. Here we need to mention how subatomic masses are measured. We can't put them on a scale to see how much they weigh, so we have to do something else. Almost all subatomic particles have a charge, positive or negative. That means they'll respond to a magnetic field. And that is how we can measure their mass, by the amount they are deflected by magnetic fields. The greater the deflection, the lower the mass. Through the years, we have worked with these charged particles. The measurement of electron masses was the most comprehensive. As we did these measurements, we found that they were deflected a little less and then a little less again. They were gaining in mass. What was happening? Remember that the ZPE waves are much more numerous on the short end of the electromagnetic spectrum. They are small enough to jiggle subatomic particles, including electrons. The stronger the ZPE, the more waves impact the subatomic particles, giving a greater jiggle. The more the electron jiggles, the more apparent mass it has. The equations of the process show that this mass is proportional to the ZPE strength squared, that is, to h squared. At this point we have both Planck's constant and the masses of subatomic particles linked to the zero-point energy. As it turns out, the speed of light is also linked to the zero-point energy. The ZPE is the parent of a number of these children effects, including Planck's constant, subatomic masses, and light speed. None of the children causes another child. They all depend on the parent cause, the zero-point energy. So how does the ZPE affect light speed? As mentioned, the zero-point energy is comprised of waves of all lengths in the electromagnetic spectrum, but there is a large preponderance of waves at the short end of the spectrum. These waves are going in all directions at once, and so are constantly crashing into each other. Think of waves on the ocean. If cross waves hit, white caps are formed and quickly die down. When the ZPE waves hit, they also have an effect. For the briefest instant of time, the impact causes a tiny energy concentration, which allows something called a virtual particle pair to form. One of the pair is negative and the other positive, and for that reason they slam back together again almost immediately, going on their way as energy waves until the next hit. But while they exist for that brief moment of time, they act like physical particles and can absorb a photon of light. When they slam back together, that photon is released to go on its way at its original speed. If there were only one virtual particle pair to navigate, that would not really affect the speed of light at all. But as the ZPE built up in time, light photons had to navigate more and more of these virtual particles, and the cumulative effect was to delay the arrival of the photon of light at its final destination. Think of a runner going over hurdles. One hurdle would not cause much delay in getting to the finish line. However, 100 hurdles would cause a great delay, regardless of the speed of the runner between the hurdles. In a similar fashion, it might be helpful to consider that it was not the speed of light that was slowing. Rather, it was the fact that the number of obstacles it had to deal with on its way was increasing. As the ZPE strength built up, space got thicker with virtual particles. Currently, it can be calculated that at any instant there are at least 10 to the 58 virtual particle pairs per cubic inch. That is the figure 1 followed by 58 zeros. Therefore, an increasing ZPE strength is the reason that the measured speed of light was slowing. So the speed of light is also a child of the same ZPE parent. We now have historical data and the likely cause of the changes in atomic constants over time. But then a problem arises. The Lightspeed data, the data for Planck's constant and atomic particle masses, all show a flattening of the trend and then a small trend reversal in the period 1960 to 1990. This is illustrated by the speed of light data 1947 to 1983 on the left, and the associated atomic data from 1950 to 2010 on the right. One reason for this flattening out can be found in the introduction of atomic clocks into laboratories around the world, starting about 1955. Atomic clocks measure time at a rate that is in accord with light speed behaviour. This means that measuring one by the other will not produce any evidence of variation in either quantity. An example of this may be seen by two bands of unstretched elastic that have a length identically marked on them. Then, both are stretched synchronously. You cannot measure the change in the stretched length in one band by the other band. Both lengths have changed simultaneously and proportionally. In a similar fashion, measuring light speed by atomic clocks will always give a fixed result. There are other factors involved which we don't have time to explore here. However, it is on the basis of data from atomic clocks that, in October of 1983, light speed was officially declared invariant in a vacuum and absolutely fixed at 299,792.458 kilometres per second. This fixing of the speed of light as an invariant quantity introduces one last major objection. This has to do with Einstein and his famous theories of relativity. For his theories to work physically and mathematically, Einstein required two things. First, that the speed of light was a fixed constant, and second, that no absolute measurements of any motion were possible. That was because his theories required that there was no universal frame of reference against which to measure that motion. For instance, you can measure a car's speed against the rest frame of a highway. But if you were to try to measure that speed from a universal point of view, his theory stated that it would be impossible to do. The reason was that his theories required that there was no universal rest frame to measure it against. So all measurements of motion are only relative, and that is how the theory of relativity got its name. In other words, if either there were an absolute reference frame in the universe against which all motion could be measured, or if the speed of light in a vacuum was not constant over time, or both, then the theory of relativity might have to be rethought. Let's take the idea of an absolute reference frame first. In 1964, scientists found that the temperature radiation depicted here was coming uniformly from all parts of the sky. It's called the cosmic microwave background radiation, CMBR. It's the echo of the original superhot state of the universe, or the temperature that is left after the universe expanded and cooled down. This background temperature is uniform to 1 part in 10,000. On this whole sky map shown here, the red areas are slightly warmer than average, and the blue areas are slightly cooler than average by this extremely tiny amount, 1/10,000th of a degree. Now here's the important thing. This CMBR does provide an absolute frame of reference. The CMBR encircles the entire universe. When anything, a planet, our solar system, our galaxy, another galaxy, anything moves, the movement has to be towards some section of the CMBR. That movement will show up as a change in temperature, both ahead of it and behind it. Ahead of it will show up as a little warmer, and behind it as a little cooler. For those familiar with the term, this is a Doppler effect. The changes in temperature can be mathematically converted to the speed of movement. We have measured the motion of our Sun in our galaxy and the motion of our local group of galaxies towards other galaxy groups against this background. The final overall result of adding all those velocities together is shown here. The direction and speed of the motion of any object in space can be different, but they can all be individually defined by the CMBR. Cornell astrophysicist Martin Harwood, in his book Astrophysical Concepts on page 178, published by Springer Verlag, comments about this important result from the CMBR, and I quote, "It is interesting that the presence of such a radiation field should allow us to determine an absolute rest frame on the basis of a local measurement." End quote. But he then goes on and tries to salvage what he can for relativity by saying, and I quote, "The establishment of an absolute rest frame would emphasise the fact that relativity is really only meant to deal with small-scale phenomena, and that phenomena on a larger scale allows us to determine a preferred frame of reference in which cosmic processes look isotropic." End quote. In other words, the CMBR does provide an absolute reference frame for motion anywhere in the universe. So Einstein's theory of relativity is incorrect, except possibly for small-scale phenomena. This also means that deriving any results using those two postulates, namely a constant speed of light and no absolute frame of reference, is also suspect. One of Einstein's strongest supporters was famous British physicist and astronomer Sir Arthur Eddington. He suggested that there was a different mechanism available which produced the same results as relativity without the need for those two restrictive postulates. He came to the following conclusion and illustrated it with an example, and I quote, "Light moves more slowly in a material medium than in a vacuum. We can thus imitate relativity's gravitational effect on light precisely if we imagine space around the Sun filled with a medium which gives the appropriate velocity." End quote. Physics now shows that the zero-point energy does precisely that. In fact, all major results of relativity can now be attained by just using the reality of the zero-point energy and its effects. This can be done simply and without the need for strange and complicated mathematics, as a number of modern researchers have demonstrated in peer-reviewed science journals over the last 20 years. As you can see, what began with my curiosity about the changing speed of light measurements started a course of research that has had some interesting consequences. It has led to an understanding of the reality of the zero-point energy, which is built up with time. This seems to answer the problems raised by the light speed and the atomic data, as it has led to the realization that atomic processes and light speed were both children of the same ZPE parent. So the conclusion is that in the past, when the zero-point energy was lower, the speed of light was faster, and some atomic processes were also faster. In our next session, we will see how these facts, along with plasma physics, can help us overcome some of the problems that we have in astronomy as far as the time question is concerned, and some other applications as well. So stay tuned for the next session. Thank you very much.